Hi everyone. So my name is Christopher, and I'm on the aluminum narwhals. And welcome to our online lessons and activities. So since this is the first week of our lessons, I'm going to explain the plan going forward and what these will generally look like. In general, you will get these videos and activities every week, with each video either expanding upon the last video or covering some new content. So within these videos, we will teach the curriculum itself and then introduce the activity for the week. And these activities are fun experiments for you to better understand what we taught in the video lessons. So hopefully you guys will be able to complete these activities with some of the materials you have at home, and it will really reinforce what we taught in the lessons. Enjoy your first week. So I'm going to start by introducing this idea known as kinematics. So physics, especially the kind that we use in robotics, is all about these interactions between static or non-moving and moving objects in the world around us. So the first thing as physicists that we need to keep track of is these objects' movements. So we have to know where the objects are. We have to know how fast the objects are going. We have to know the direction of the object. And so this gives rise to the first essential component of kinematics, which is keeping track of an object's position. So as I'm sure you guys are all aware, position is measured in units of distance. So things like feet, meters, etc. So position can be quantified using a collection of measurements called coordinates. So let's say we have a beach and we have a man named Bill. And Bill sees a narwhal. And this narwhal is 1,000 feet west of Bill. And it's not going to be to scale, but the narwhal is also 1,200 feet west. So this can be represented using coordinates in a coordinate plane. So we have 1,000 feet west, 1,200 feet north, and this would be the position of the narwhal if Bill were at the origin. But we live in a three-dimensional world, so not only do we need to keep track of two dimensions, we need to keep track of this third dimension. So let's say that now Bill is on a mound. And Bill now has some height. So let's say there's 50 feet that Bill is above the ground. So now our coordinate would need to be 1,000 feet west, 1,200 feet north, and 50 feet below. But robotics is pretty much only in two dimensions. Well, we actually only need to really worry about two of the dimensions since most of the time the robots are on the flat ground. So we're just going to stay in two dimensions for now. So we're talking about position, but these objects don't just stay in one place. They move around, right? So this gives rise to the second crucial aspect of kinematics, and that is motion. So in order to describe an object's changing position, we need a new concept, speed. And speed is defined in a way that speed is equal to distance an object travels over time. So, for example, speed can be miles per hour, which measures the speed of your car. So, let's say now we have a car. And this car is, this car is traveling at 65 miles per hour. And so if we start from the starting line and we travel for 1 hour, the car will end up 65 miles away from where the car started. And by that same logic, after 2 hours, the car will have gone 130 miles. So now let's go ahead and draw a graph for this scenario. So on one axis we have time, and on another axis we have distance. And I just mentioned that after 2 hours, after 2 hours, the car would have gone 130 miles. We'll go ahead and plot that. And this, of course, is in hours. And this is in miles. And after 1 hour, the car will have gone 65. So 65 and 130. So after 1 hour, 65 miles. After 2 hours, 130 miles. So let me make it a little bit straighter. So that is our line that would represent the situation. But what do you guys think the slope represents in this scenario? Well, slope is rise over run, right? And our rise is 130 miles. Run is 2 hours, and this equals 65 miles per hour. So our slope of distance versus time is our speed. But let's say we have another car. And this time, the car is not going forwards, but the car is going backwards. So how would we represent this? Because the speedometer on the car will still say 65 miles per hour. And after an hour, it would still travel 65 miles. But the problem is the car would still be going in the opposite direction. So this is a big difference, and we have to specify this. And this gives rise to a new concept known as velocity. So before we had speed, and now we have velocity. And velocity has a direction component. So not only does it represent the speed, but it represents the direction of motion. So this car is going 65 miles per hour backwards, and this other car is going 65 miles per hour forward. Or oftentimes physicists like to represent direction by assigning a positive and negative value. And this makes it a little bit more concise as opposed to saying 65 miles per hour backwards or forwards. So instead of saying backwards, they say negative 65 miles per hour. So a crucial concept here is velocity represents direction, and that therefore makes it a vector quantity. So velocity is a vector quantity. So what does that make speed? Well, that is now a scalar quantity. So the same kind of sign distinction can be made when we are talking about differences in the position of objects. So distance and displacement are very similar to speed and velocity. Distance is scalar. It's a scalar quantity, whereas displacement is a vector quantity. Meaning that if I were to walk 400 feet backwards, the displacement would be negative, but the distance would be the same regardless if I were to have walked forwards or backwards. So displacement is a vector, distance is a scalar, similar to speed and velocity. So that's an important distinction to make between those two quantities. But things don't maintain a constant speed all the time. There's also a speeding up and a slowing down. And this is acceleration. So acceleration is to velocity as velocity is to position. So what this means is that acceleration, which I'll represent as A, is defined to be the change in velocity. This means change in, or delta, velocity over change in time. So this is another way of saying velocity, or velocity per time, or velocity all over time squared. Position, excuse me, small position. Position. So, note that just like velocity and displacement, acceleration is a vector value. So, acceleration takes into account direction. So now let's change the scenario that we had before. So let's say now this car is going on an on-ramp. So we have our on-ramp. And the car is now going onto this on-ramp. And when it goes onto the on-ramp, it accelerates. So it starts at, let's say, 30 miles per hour, and it ends at 65 after it's done accelerating. And so obviously anytime you've ever merged onto a freeway, you've experienced fairly rapid acceleration. Because you start at about 30 miles per hour and you end at about 65 miles per hour. So what's our acceleration in this scenario? Well, again, acceleration is change in velocity over time. So your velocity is already starting at 30 miles per hour, and then it's going to 65. So from 30 to 65 after, a couple minutes. So let's just say like minutes, after 1 minute, you've accelerated. So that's once again a straight line in velocity versus time, and acceleration is your slope. And so your acceleration would be your change in speed, 65 miles per hour, minus 30 miles per hour all over your time, which is 1 all over 60 hours. And so that would be your acceleration in this scenario. So now I'm going to go into the activity that you guys will be doing this week to sort of reinforce this topic. So the activity for this week is to measure the movement of a toy car using a measuring tape, a stopwatch, and you need a smooth surface. And you need to go ahead and follow along with these instructions. And you'll really be able to practice some of the ideas that were taught in the lesson, and you should get a better understanding of distance and displacement and velocity and how they all relate. And there's a challenge at the end, and so have fun.